All right, folks. So today we're going to talk about rhythm engineering in-sync system. In-sync happens to be the most widely deployed adaptive control system in the North American market. Before we get into any of the actual details, I want to take you through a little bit of a tour. I want to talk about what we're actually seeing out there in the real world, i.e., when we look at traffic, what we're looking at is local problems. However, they have a global impact. From a local problem perspective, we're looking at things like $150 billion in wasted time and fuel, over 80 billion pounds of carbon emissions. I think more importantly is the idea that we have somewhere between 30,000 and 40,000 motorist deaths per year. In fact, the Federal Highway Administration has given the whole traffic signal timing a D+ grade. Now, a D+ grade really means that we need a lot of improvement. So how do we get to where we are today? Well, that's not our CEO there, but let's pretend that's our CEO. As a matter of fact, let's pretend that's you. You're the engineer who's taking calls on a regular basis. You are the person that's getting the phone calls from the motors. They're complaining to you. Why am I stuck at the light? Why is the light skipping me? There's nobody coming in from the other direction, but yet I'm still waiting. So that's exactly what our CEO was doing. Our CEO is the founder of the company and the inventor of the product. And he was a bit surprised that when he looked at this, he really did not find any solutions on the market to solve this problem. When we start getting into more of the actual detail of the product, I'm going to describe to you what I like to call simple elegance. All right, because once you see the solution, you probably, as an engineer, you probably say, hey, that's a great idea. How come I didn't think about this? But that's what we're going to do, and that's why I like to call it simple elegance. I'm basically going to transform the way you think about traffic today into a completely new model. So when we start looking back at what our CEO was thinking in the beginning, his thing is, how do we make life better? How do we make the environment better? Which kind of leads to our mission statement. And our mission statement is very simple: bringing our loved ones to their destination safer and faster. So everything we do at Rhythm, everything from a product perspective or a software perspective, really comes down to the idea of bringing our loved ones to their destinations safer and faster. That's what we want to do. That's what our mission is. So, as I mentioned a few seconds ago, InSync is really the most widely deployed adaptive system in the North American market. So what does that mean? Well, before we get into the actual details, before we get into some of what the product actually does, let me tell you about the impact, i.e., what's happened from a implementation perspective, what happens at the intersections and the corridors where we have deployed InSync. I guess one of the first case studies we'll look at is Jordan Creek Town Center, very major retail space, very busy off-ramps off the I-80, and they had seasonal time of day traffic, which means, of course, it always changed. It also means that there was a lot of saturation and backup. At this particular deployment, we actually received a nomination for Innovator of the Year award because we showed up to a 22% decrease in time delay, a 12% improvement in fuel economy, and corresponding drops in calculated emission. So as you can see, some of the metrics here are pretty impressive. Let's move on to a different case study now. Let's look at Pennsylvania, Upper Merion Township, where we have one of our first implementations in the King of Prussia area. King of Prussia Mall, you may or may not know, is probably one of the biggest malls in the country. And even here, I mean, I'm not going to go to the everything on the particular slides, but here we've observed a 33% reduction in travel delays. And this is only in 2 intersections. We've also observed a 20% reduction in stops. Before InSync, we were at a 1 minute and 45 seconds. Before we're at 1 minute and 10 seconds. Obviously, in the world of traffic, 35 seconds is really quite a bit of an improvement. I have a couple more case studies to show you. I'll go through them. Again, I'm not going to go into a lot of detail, but if you have any questions, please feel free to stop and let me know. Another case study we have here is San Ramon, California. Here, we're going to look at emissions reductions. What we've done here is after the implementation, we have a 38% reduction in emissions over a total of 5 intersections and a little bit over, over half a mile. That's 114 gallons of savings in fuel and almost 30,000 gallons of savings annually. One of the other case studies that we like to talk about is La Jolla Parkway. La Jolla Parkway is a very busy corridor. If we take a look at the aerial view, you can see that it actually leads to the beach. San Diego wanted to give us a condition where it was really difficult for anybody to work with. So they gave us a challenge, and Rhythm accepted that challenge. So what we observed after implementation, again, you'll see some pretty impressive metrics here, is eastbound AM and PM, westbound AM and PM. We have delay reductions and stop reductions. And again, we're looking at a 48% reduction in the morning eastbound, a 5% reduction in the afternoon eastbound. Again, I'm not going to go through all the numbers here. You can see them for yourselves. From a stop reduction perspective, eastbound in the morning, 44% reduction, and again, 28% reduction in the afternoon. So again, the metrics speak for themselves. Now, in addition to that, what else has happened? Well, what we're looking at here is average speed increases. We've actually increased throughput. We've reduced the travel time to get from point A to point B. 40% increase in the morning, and again, a 5% increase in the afternoon. And keep in mind that what we're talking about here is what used to be a very congested, very saturated environment. If we take a look at another aerial view, and we start looking at the what it looks like, can you see my cursor? I assume you can. If you take a look at these red items here, this is a before picture at about 9:31 in the morning. The red indicates the heavy saturation of the traffic along the corridor here. After implementation, it actually looks like a couple of weeks later, you can see that all the red has practically disappeared. InSync has actually gotten rid of that congestion, pretty much eliminated the queue that existed. You can see the same thing here at a different date and time. Okay, June 9th, we see more congestion. A couple of weeks later, we see it practically eliminated. So that's what we're seeing. A couple of things to point out is a lot of the numbers that I'm talking about, a lot of the metrics that we're seeing, keep in mind these are not our metrics. These are usually performed by the agencies in question. In fact, one of the ones that I like to talk about is the Virginia DOT traffic study. The traffic study itself is somewhere around the 70 to 80 pages long. Some pretty good reading for you engineering folks. But again, if you want to look at it, it really has all the information you need to back up the numbers in their particular corridors. 67% decrease in stops, 58% increase in speed. Again, not going to go through all the numbers. What I'll actually do is after our meeting, I will provide for you a copy of the study so you can take a look at it yourself. But of course, we can dollarize everything, and if you look at the actual benefit over cost calculation, you see that we have a travel time benefit here of over annually over $43 million, based on an initial system cost of almost $5 million. So that is a pretty good return on your investment. Any questions? If no questions at this time, I'll move on. As I mentioned, I will send you a copy of the studies, and as I mentioned a couple of minutes ago as well, all the numbers that we talk about, whether it's stop reductions, delay reduction, and so on, these have all been verified by third parties. This is just a listing of some of the consultants that we work with and have produced their own independent studies. I will send you the Virginia DOT study, but at the same time, I'll also refer you to our website where you can download some of these studies yourself, which is probably a good idea if you want to look at some of the independent verification. So let's talk about a little bit more about InSync, or rather Rhythm, the company. Currently, we are deployed in over 2,500 intersections nationwide. We are also starting to deploy in Canada as well. We have a couple of different implementations on there. And in fact, Currently, we are working on getting a very large project up in the Toronto area, somewhere around 500 or so intersections. But again, I think the key item here is that we are the most widely deployed from an agency perspective, and I think that's critical. Now, I'm going to go into the actual product. Before I do, and I actually don't have a slide for this, but I want to talk about a couple of different things that I think are critical. As a salesperson, I'm all about differentiation. I'm all about what makes us different than everybody else, and why I need to show you the value of our product, or how I show you the value of the product. So a couple of the things that I talk about is the idea of real time. Now, when you speak to anybody else, or anyone, in fact, any other adaptive vendor about real time, everybody's going to tell you, yes, we are a real time adaptive system. But you have to ask a few more questions. What does that actually mean? Well, a real time adaptive system, somebody's going to say, well, we collect our data in real time. Well, that's great, because you know what? We all collect our data in real time. Every time a car goes through a loop, every time a car gets spotted by a camera, that data is collected in real time. But the more important question is, when is that intersection or the car actually optimized? In our system, which is a true real-time system and the actual only real-time system on the market, we optimize that on a second-by-second basis based on the real-time information that is collected. So we not only collect data in real time, we also optimize the traffic in real time, or we optimize the intersection of colors in real time, which is very different from other systems, because other systems, although they will collect data in real time, what they'll also do is they will optimize the intersection really based usually after a complete cycle has passed, sometimes more. And in the world of traffic, when we're talking about 30 seconds or 120 seconds, that's a lifetime. So when a system, which we like to refer to as responsive, is making decisions for traffic based on all data, obviously that's not adaptive. So let's get into a little bit more of the actual how the system works, and I'm going to take you into that right now. So there's three things I want to talk about. The three things you see here. We're going to talk about the idea of analog to digital. Again, we're going to go into a little bit more detail as we progress, but very simply, analog to digital simply means we are going to change the traffic model that you were accustomed from the early 20th century to what I think is a revolutionary model, and I'll explain to you how we're going to do it. Local optimization really revolves around the idea of putting intelligence at every intersection, where our system is going to look again in real time and make decisions in real time. Of course, typically when our system is installed, it is not done on a single intersection. It is done along multiple intersections along the entire corridor. And for that, we use the idea of global optimization, getting traffic from point A to point B as quickly as possible and as safely as possible. So we're going to go into more detail in each one of these points. And again, the thing to remember here is that these are the three things that our system does. So let's talk about the idea of analog to digital. I'm sure some of this looks familiar to you. The whole idea of analog to digital is really very, very straightforward. If we take a look at the analog controller on the left versus the digital controller at the right, when we talk about the idea of going from analog to digital, what we're saying is we're going to change our traffic model, because in today's world, in today's environment, every single traffic cabinet that does not have InSync installed, although they have this beautiful modern digital computing equipment inside the cabinet, everything that you see here with this beautiful controller on the right, it does nothing more than emulate what this old analog controller from the 20th century is doing. It does the same thing day in and day out. All right, so we are going to change this model, and I'll explain to you how we're doing that. A good way of explaining that is by considering this particular example right here. If you think of your old-fashioned TV, the old-fashioned TV, besides the fact that you have to get up, you also have to, if you wanted to go from channel 2 to channel 13, what you would do is you flick the channel from channel 2 to channel 3 channel 4, until you finally get to your desired channel. That is very similar to the existing traffic model today outside of rhythm technology. Everything is sequential, everything is fixed, and if you consider a traffic model, it does this day in and day out, 24 hours a day, 7 days a week, 365 a year. It's limited by the whole idea that everything is sequential and everything is always fixed in the way it works. If we start taking a look at the first adaptive control system back in 1920, I'm going to describe to you how our system is different and why we are a real-time adaptive system. So consider this slide in front of you. Back in the 1920s, out in Detroit, we have a person out in the middle of the street, and as a human being, I mean, it really can't get more intelligent than a human being. A human being is facing traffic in every direction. That human being is looking at traffic coming from one direction and says, okay, there's nobody coming from here, so let me just stop that and let the other direction go because there's more traffic there. So as a human being, I can see in real time what's happening all around my environment, and I can make decisions based on that. That's exactly what our system will emulate. So again, just going back to the old system, I've already described the idea of the getting up and turning channel. So what I'm going to do is I'm going to describe the whole idea of what happens with InSync, with our traffic model. And here, as opposed to the old system, now that we have 500 channels and nobody watches, if you want to go from channel 5 to channel 500, all we have to do is click in 500 on our control, and we automatically get there immediately, in real time, when we want it, as soon as we want it. As opposed to the old-fashioned model here on the left, where, again, everything is sequential, everything is fixed movement, fixed timing. So think about that when we start describing how our system works. So we look at our system as a true digital state machine. And the reason we say that is because our system is maintaining the complete configuration. It maintains track of everything that we want to happen at that particular intersection. So if you look at your traditional intersection with 8 faces, and we start looking at what's happening there on a 24/7 basis, 365 days a year, we know that when we go to a particular intersection, what's happening here is all the movements there, all the faces start from your left bound, and then it may go to your next particular set of phasings. Eventually, it's going to cross a barrier, and it's going to do exactly the same thing over and over again. But it's going to be in a fixed sequence, fixed timing. Again, 24 hours a day, 7 days a week. If we now start considering what the InSync traffic model is like, we're going to look up here where we have our left turns. In the traditional traffic model, if we start looking at what typically happens, and let's assume that this particular phasing is key, such as A1, A2, and so on, although we may start at A1, the next logical movement based on our 20th century traffic model would be we're going to go to the straight movement on A2. However, based on the current traffic conditions, what my system is seeing today, based on the intelligence, based on the data that it's receiving, it's determining that instead of going through my straight through up here, we are going to do this. So we're going to jump directly from A1 directly over to C5. And why? Because that is what my system determines is the appropriate thing to do based on current real-time traffic conditions. So if you think about this for a second, we've pretty much, no, not pretty much, we have eliminated the 20th century traffic model where everything is fixed phasing, fixed timing, fixed sequencing. Now, we've gone from that to really dynamic sequencing, dynamic timing, again, because that is what we require based on real-time conditions. Now, before I go on, because this is one of the first objections that I hear is, well, what about safety? Well, here's our take on safety. We feel that this actually increases safety because if you start thinking about your typical motorist sitting at the intersection that has been driving day in and day out week after week, month after month, year after year, what he or she is going to see is they're going to go to a light. They know exactly what's going to happen. They know exactly how long they have to wait. So they're going to go in there and they're going to pull out their BlackBerry or their iPhone and they're going to start looking at their Facebook account and they're basically going to start paying attention to the road. In our case, now that we have communicated to the community that things are going to be different and it will not be as fixed as before because the decisions are going to be made in real time, we are forcing the motorists to actually pay attention. So we've gone from motorist traditional expectation to motorist awareness, therefore increasing safety. And I like to talk about that because frankly, that's one of the objections that I always hear during my meetings. So how do we do all this? Well, what we do is at every intersection along the corridor, we're going to put up a camera. In this particular image here, we have a standard video detection. It could be thermal. Probably towards the end of the year, sometime around 2018, will also include radar. And what that's going to do is this is going to face the incoming approach and is going to collect the data. It's going to collect the data. It's going to send that data over to our processor. That processor is then going to look at the data, optimize it, and then what it will do, it will pick a specific phase pair and only a single phase pair, again, based on the real-time environment. And then it will send that information over to the controller, which happens to be running free. And that's all that's happening. By the way, this is one of the reasons that during the end of my slide deck, I'm going to tell you that we are eliminating transition because the controller is only seeing it what we're telling it to see. Any questions on this so far? All right. So this is how we actually do it. The next thing we're going to talk about is the whole idea of local optimization. And again, local optimization is the idea of putting intelligence at the individual intersection. So at the individual intersection, again, we have our system. I explained to you a little bit of how that works. And the one thing, again, as a salesperson, what I'd like to point out here is the value. One of our things that our system does that other systems do not do is not only are we creating detection zones on a per lane, per approach basis that our system can look as far down as the eye can see, but we are also looking at the real-time queue, how many vehicles in each lane and each approach, and how long those vehicles have been waiting. We are managing that information, and that queue and delay analysis is what adds to the value of our product. So how does it do this? Well, very simply, what the system is going to do is every time a vehicle comes into the lane, into the approach, the system is going to provide a token. Every time that vehicle has been sitting there for more than 5 seconds, it's going to provide another token. Now, we like to call it a greedy algorithm. Let's assume it's that cop, or let's assume is that traffic person or our system there. What's actually happening is this person or our system is saying, look, I'm greedy. I want to keep as many tokens as I can to myself. I'll give some out, but eventually I want them back, and I'm going to decide exactly when it is that I want these tokens back. So at the intersection, what's going to happen is, as you can see from the representation here, every time a vehicle comes in, it's going to increase the token. Every time a vehicle is waiting, is going to increase the tokens again. Eventually, what the system is going to say, hey, I've given out too many tokens. It's time to get him back, which really means it's time for me to serve this particular traffic. So if you look on the upper left-hand corner in this particular example, the traffic is going to start moving because that's what our system has determined based on the real-time data. So again, we've gone through this. I'm not going to really delve into this any deeper than I have before. But again, it's the idea that we've gone from our standard 24/7 by 365 20-center traffic model where we go fixed cycling, to a dynamic cycling, dynamic sequencing. So in this particular case, as I mentioned before, rather than go from these left turns over to my straights, okay, what I'm going to do then is I'm going to go to a total different phasing. If for some reason my system determines that we need to skip a phase, sure, we'll skip a phase as well. That's what our system does at every intersection. So we've talked about the whole idea of going from analog to digital. Again, that's the idea of eliminating the 20th century traffic model of fixed sequencing. We're now talked about local optimization, the idea of applying that analog to digital and really using the dynamic sequencing as our real-time data requires. So now what we're going to talk about, as I mentioned before, again, we're not usually talking about a single intersection. We're talking about an entire corridor. So let's talk about global optimization. Global optimization really is the idea of getting traffic from point A to point B as quickly and as safely as possible. So if you start taking a look at this particular slide here, the first thing I'm going to point out to you is let's look at our pavement here, at our traffic road here. As you can see, it's all blank. Now, before I get started, I want you to think of this as open space, open time, kind of like a calendar. First, the whole idea of the global optimizer is to schedule mainline progression. At some point during our implementation, what's actually going to happen is that our engineers will get together with your engineers. We'll collect some data that you may have, such as sync or green data, for example. We'll analyze that data. And then what's going to happen is we're going to make a determination of what the proper tunnel will be, i.e., what is the proper size to allow a platoon of traffic to get across from point A to point B as quickly as possible. If you take a look at this particular animation, what's happening here is here's a platoon of traffic coming down the ways, and of course the side streets have stopped. The system can determine that the traffic is there, but at some point, of course, that corridor is going to be blank. This is going to allow us free time. Now that we have all this free time available, this is when our system will be allowed to service the side roads. So not only are we guaranteeing mainline and bidirectional progression along the main corridor, okay, once we serve that, we allow the system to intelligently serve the local streets as well. And of course, that's critical because we want to make sure that that everybody is served appropriately. So this is the whole idea of the global optimization. This is how it works. We're guaranteeing green time for the mainline movement. We're creating platoons of traffic with the green tunnels. And again, we are making sure that that the side streets are serviced as required and appropriately. So all of the phases are going to be served during that non-coordinated, unscheduled time. A different way, a slightly different way to look at this, again, is through the use of a calendar, if you will. If we take a look at a couple of different intersections, and we start creating that tunnel, westbound and eastbound, let's say in 30-second intervals, we're going to create this tunnel. And obviously, on this particular intersection, we are going to repeat these patterns across all my allowable time. Okay, and what's going to happen here is we're going to be serving westbound and eastbound traffic. And if you look at this picture, we obviously don't have to serve both directions simultaneously, which is the beauty of the whole idea of the digital architecture, i.e. the dynamic sequencing, dynamic phasing, because we're not limited to, again, always using the same phasing at any particular point in time. So in this particular case, we've scheduled for the intersections. We've done the same for the intersection 2 and intersection 3. As you can see, they have been configured slightly different. Again, based on the data that we have received, I think the critical information here is, again, we do have all this white space available here where we service the local streets, and keep in mind that we are talking about an adaptive system. In this particular case, in this space between the tunnels, keep in mind that we have the ability to actually configure this and change this dynamically as required based on your existing traffic conditions. So if for some reason we need to change the size of the tunnels, whether we need to increase it in one direction or we need to decrease it in a different direction, the system allows you the ability to actually do that. So when we look at this and we put this all together, we start connecting the dots, and what we actually have is really an upside down time-space diagram with again the idea that what we're doing here is serving the movement based on real-time conditions, getting the traffic from point A to point B. And again, critical is because we're adaptive, because we are dynamic, we do have the ability to change the size of those tunnels as required based on the current traffic conditions. So, in a nutshell, at a very high level, that's how the system works. Now, in addition to that, one of the some of the other items that I like to talk about is again the idea of failure mitigation, because we're talking about safety, we're talking about motorist lives here. So how do we manage for that? Well, a couple of things to look at is one, from a processor perspective. The processor always has control of the intersection, unless, of course, we have some issues such as networking down situations. We have a catastrophic processor failure. In that particular case, keep in mind that what's going to happen is that, and just a quick caveat here, we have to determine this during the initial implementation because we have to put this in the actual configuration. So if we have a total processor failure, for the lack of a better term, the control reverts back to your existing controller to control traffic operations. Okay, in the situation where we may have a network failure, the system can go back to historical data. So we can look at 9 a.m. at last Tuesday, and we can make a determination of how to serve the intersection based on that historical data. Nonetheless, the system still continues with coordination and still continues with local optimization. So even though we may have different types of failure, where there's hardware failure, where there's network failure, the system still adapts and still allows us to manage those intersections and manage that entire corridor. All right, so how is InSync different? So in the beginning, I spoke to you about a couple of different things. I spoke to you about the idea of real time, and I spoke to you about the idea of responsive. So when we start looking at your typical responsive system, we are looking at what we call second generation system. These systems use data based on trends, they use limited information, and they also require a pretty large investment as far as additional hardware infrastructure. If you recall, when we were talking about local intersection, we're using thermal, we're using radar. In the future, we're using video. Keep in mind that we are looking really at a complete field of view, a line of sight type of scenario where we can see everything that's happening coming down that particular corridor. Whereas in a second generation system, we are really going to see only limited information. In this particular case, we do have some additional infrastructure here, so therefore we can see that, but the bottom line is until that traffic actually gets to this additional infrastructure, we really don't see it, which again is totally different than the kind of systems that Rhythm is talking about. You know, we have a stop bar, we have an advanced bar, upstream and downstream detection. We start talking about a lot of money here. So those are some of the issues with second generation adaptive systems. And again, it's not seeing all the information, and it's using a lot of historical trends because they're responsive instead of real-time data. So if we move on a little bit, let's talk a little bit more about InSync and again, third generation adaptive systems, or frankly, what I like to refer as an actual adaptive a real-time adaptive system versus a responsive system. In this particular case, we have the InSync detection, which can see as far as it needs to. There's no reason for that additional infrastructure, so we can really see everything, make determinations based on a lot more data than your typical second generation system. So as traffic is coming by, we see the traffic coming by, we know where the traffic is headed, we know where it's coming to, and depending on the individual approach, we will serve that approach accordingly based on the data that's being collected, without all the additional infrastructure, without all that additional expense. So those are some of the differences that I like to point out. Also, more specifically, I take it back to the whole idea of responsive versus real time. Again, I've kind of gone over this over and over again. The key item on this particular slide is that your typical responsive system is not going to make a decision based on real-time data. There's going to have to be at least a minimum of wait time for a complete cycle. The responsive system will be making decisions based on all data, whereas the actual in-sync system will again collect data in real time and more, just like everyone else, okay, but more importantly, is going to make decisions based on second by second real time information. It's going to also manage the queue, determine how many vehicles, not just stop bar detection, mind you, but how many vehicles are waiting for us in that queue and how long they have been waiting. That's all critical, and that whole live queue and delay assessment, that's all part of the additional value brought to you by our real-time adaptive system. So again, something to consider. When we walk out of this room today, I want you to think back to the idea of responsive and adaptive, and I want you to think back to the idea of both the real-time data collection and the whole idea of the real-time intersection optimization. Those are the big differences, and those are that's where we bring in the value. Again, dynamic sequencing, no transition. Remember that image I showed you a while ago, because our control is really determining it, or rather our processor is really determining what's happening and is telling the controller what to do. So therefore, we are eliminating the transition. Any questions on any of this so far? Okay, if not, we'll basically just move on. Again, I don't want to really go too deeply in this. Frankly, the idea here is responsive versus real time. Of course, I've demonstrated to you, or I've shown you the idea of how our system works. One other thing to consider is our software behind it. We're going to talk a little bit about our software called InTraffic. InTraffic basically is our system, which is our software system, which is web accessible. It allows you access to everything on our intersections on our corridors using any typical web-based device, whether it's a notebook, a standard desktop computer, a phone, or a tablet. You can look at all the data in our system. What our software is going to do is basically going to continuously look at this data, is going to aggregate data from all the processors and the controllers that are out in the field, and is going to present the data to you in meaningful graphs and tables for easy analysis. So it's not only going to present the data, but it's going to really turn that data into information and make it actionable data. Because, I mean, really, if you think about it, collecting data without really having the idea to act on the data is fairly useless. So our software allows you to actually look at this. It allows you to create some what-if scenarios, spot areas that may require attention, and really lets you make those changes in simulations and lets you change the configuration accordingly. You can tweak any of the information in the configuration, and then check to see what would happen before you actually deploy them to your systems. If you think about it like a sandbox where you can do some testing, this is what the system allows you to do. And again, just looking at the screenshots, you can see that it's very graphically oriented and very user-friendly. Taking a look at at how you create some of these intersections, how you create some of these configurations, really allows you to do drag and drop or drag and click. It lets you go through the individual intersections, put them in there, and plot them directly on a map, and then let you view the configurations and make the changes accordingly. As you saw from some of the other slides before, you can get some real-time visual monitoring. Now, just a quick caveat on here, because again, this is one of the questions I get. What you're seeing here really is your traditional video imaging. Of course, if you're looking at radar or if you're looking at thermal, you will not be seeing it this way. Thermal imaging really is more coloring, hot spots versus cold spots, so you really don't get to see this. Your typical chief of police or traffic person sitting at some center may want to look at the individual intersection, and they can with our standard video. But again, when it comes to thermal or radar, it's something not the kind of view you'll be able to get. So again, quick caveat, but you do have access to real-time visual monitoring. Another piece of our data really is our inform system. Really, this is a data visualization tool which collects the data, creates graphs for you, and provides data again in a more visually, let's say, easier to see graphic. So whether you're looking at your different green allocations or your capacity of your degree of saturation, they can look at all the data and visualize it for you without you having to work through spreadsheets and typical textual information. So from a support perspective, we provide 24/7 by 365 support. You can call us 24 hours a day. You can email us 24 hours a day. This is guaranteed and comes as part of the standard warranty. That standard warranty is 2 years, by the way. And basically, just think of our rhythm engineering team here in our office as part of your support team. What's going to happen from a support perspective is you'll create a case. We'll analyze, see what's happening in our system, and we'll let you know what you need to do. And we'll also train you, of course. And there are many situations where you'll be able to make some fixes yourself. But in some cases, for example, if it's a hardware issue, we'll determine that for you. And again, because you are part of because the system is part of a warranty for 2 years, we'll simply go through an RMA process and replace the equipment for you as well. Now, we of course have our customers who can provide some first-hand information. Again, I'm not going to go through all of these particular slides. I'll let you look at it, but very simple. One of our customers is telling us it's like having our system is like having several extra traffic engineers on staff. Okay. This one is telling us again. I'm not going to go through it, but they're getting less calls. They're getting more positive feedback from the community, and they're seeing the return on investment based on our system deployment. Okay, I have a couple more. I'm just going to put these up here for a couple of seconds. If you have any particular questions about a particular slide you see, please let me know. More importantly here, Linda Voss from Topeka, Kansas is telling us that the number of stops is way down, the congestion is way down, and more importantly, is a lot safer. So how sure are we at this? I mean, we'll for the lack of a better term, will we put our money where our mouth is? Well, the answer to that question is yes, we will. This is the InSync promise here. If after 3 months of adaptive operations, you do not feel that our partnership has shown an improvement in the metrics that we have spoken about, we will issue a full refund on our system. That's how sure we are that our system will provide an improvement. And we will guarantee you that at every single implementation that we do for you, we will guarantee improvement in every one of the metrics that we have spoken about. I don't think there's a vendor out there that can say that to you. But the bottom line is we are so completely sure of our system that we are willing to do that. So in summary, we're the only company that does that. Again, from a 20th century perspective, we eliminate transition. We eliminate the whole idea of fixed cycling, fixed sequences, the whole idea of ring-based limitations, and of course, we are not using time-of-day plans. So again, when you look at this particular slide, these are the things that you see every day, 24/7, 365 days a year, simply based on the original traffic model. We're eliminating all this. Instead, what we have here is we have real-time demand input based on that the input system that we discussed. Again, radar, thermal. Again, radar is in the future, thermal and video. but our system is immediate adaptation. Again, I have to keep stressing the idea of real-time adaptation based on real-time data, which is an adaptive system versus a responsive system. I have to keep stressing that because that is the value of the system, and that is one of the key differentiators of the system. Dynamic sequencing. Dynamic sequencing eliminates that whole following the exact same phasing 24/7 and adapting to the current traffic condition in real time. Bidirectional progression. It doesn't matter how great the engineers are and how amazing their timing plans are. Bidirectional progression is very difficult to achieve. Our system makes it easier. And of course, as you can probably derive just from the presentation, our system is very flexible. It will adapt and change based on the current demand. And of course, keep in mind that I don't know how we lost it, but hold on one second. Keep in mind that, pardon me, okay. Keep in mind that our system will change based on the demand, so we don't have no time, as I mentioned before, no time of days plans, no ring-based limitations, and so on. So that's it at a high level. I've introduced the value of our system. I've told you what makes us different than everyone else out there, and why we bring a completely revolutionary model to our system. So from this point on, I'd like to take a few minutes to go through some questions. Please feel free to ask any kind of questions you want. We can definitely go into that. Before the end of the presentation, I'd like to reserve at least 5 or 10 minutes. I have some questions of my own. I'd like to talk about possible next steps. I'd like to talk about perhaps you have some projects coming up. Maybe there's some areas there where we can help. So that said, that brings an end to my presentation, and I'll turn it over to you folks. Thank you very much for everything, and that's it. Okay, right, I don't know Cesar, what to do here.
Great job. Sorry, I was trying to find the unmute button. I'm going to stop the recording.